Today we're going to be talking about enzymes. You've heard about some enzymes. We talked about them in our DNA unit, in our digestive system unit currently, and today we're going to break down exactly what an enzyme is and how it works. So the first thing we need is a definition. An enzyme is an example of a protein. We learned about carbs, proteins, and fats. An enzyme is a protein, so that means it's going to have an N, a nitrogen in it. So it's a protein molecule and it speeds up chemical reactions. If you take a chemistry class down the road in college or AP chemistry, you'll learn a lot more about how exactly enzymes work. We'll do the basics today, but there's a lot more to it. So what enzymes help us do is they speed up these reactions, and the goal of a chemical reaction is either to make something, we're either combining molecules, remember we talked about glucose combining or hexagons combining, or we're breaking something down, like in digestion when we're breaking apart molecules so that the body can use them. So another way to say that we speed up chemical reactions is to say we build things up or break them down, because that's what a chemical reaction does. Goal of a chemical reaction, combining two things or breaking them down. So I have a couple pictures down below. I'm not going to get into this last one just yet. But here we see a red and a green dot. They're representing molecules. And this is the enzyme, and they're combining. They're going into this enzyme, and they're coming out as one. So this enzyme is helping connect them. Over here, we've got one molecule going into the enzyme, and the enzyme's helping to break that apart. So enzyme can really help do either thing. Enzymes often end in ASE. I have some examples down below. Helicase unzips DNA. Polymerase helps add new nucleotides to DNA. That was way back in our DNA unit. Lipase, we're going to learn about it, digests fats. We know amylase already, digests carbs. The one protein we learned about was the one in the stomach, pepsin, that digests proteins. That one does not end in ACE. That's kind of one of the few exceptions here, but most of the time they're going to be ending in ASE. Let's take a look at this graph. Okay, what we have on the left is our enzyme activity, how much that enzyme's working. Then we've got temperature. Notice, there's certain temperatures this enzyme works really well at. What temperature does this enzyme work really well at? You might say 40 or 50. That's where its activity, its ability to break things up or build things is really, really high. Where does it not work so well at? Maybe you would say 65 or 0 degrees. So temperature really affects an enzyme. Let's look at that in a second here. So enzymes require a really specific temperature. They also require a really specific pH, and we'll take a look at that in a second. What the heck is pH? pH is how acidic or basic the environment is. So if it gets too hot or too cold, or too acidic or too basic, the enzyme's not going to work properly. It's kind of like Goldilocks and the Three Bears. Can't be too hot, too cold, has to be just right. Why do enzymes not work too well then? Well, what happens is our enzyme molecule here, this green guy, when it's really hot or it's really acidic or really basic, it actually changes the shape. And we're going to talk about how all this works, but this molecule has to fit in like a puzzle piece. And when it's really hot or really acidic, it changes shape, and now this molecule doesn't fit in there, and we can't break that molecule apart or build it up. So let's take a look at these graphs that show pH. So notice here we've got two different enzymes. We've got pepsin. We know pepsin works in the stomach, and trypsin. We haven't heard of that one yet. But this now is showing us pH down here, and this is showing how much that enzyme's working. So if we just take a look at pepsin, which pH would you say pepsin works the best at? You might say somewhere between 2 and 4, maybe around 3. Now I have this little pH chart down here to help us. A 3 is right here, and it's in this acidic range. So a pH of 3 means The environment is acidic. Well, if we take a look, the stomach has a pH of 2, which is really acidic, and we know that the stomach has acids in it. So is it a coincidence that pepsin works really good in an acidic environment and it's found in the stomach, which is acidic? It's not a coincidence. These enzymes probably evolved to exist in these locations where they work the best. So pepsin requires an acidic environment, therefore it's in the stomach, which is acidic. Let's look at trypsin now. Trypsin's this other one. What pH does trypsin work really well at? Probably say somewhere around 8. If we look at 8, 8's neutralish. It's pretty close to neutral. If we look at the pH of our small intestine, which is where trypsin works, look at the pH of our small intestine is 7 to 8, which means trypsin is found in the environment that it works the best in. If we take trypsin and move it to the stomach, where the pH is over here, it's not going to work very well. So the pH and the temperature are super important. Let's talk about some examples of enzymes. We've already talked about 2, and so we're just going to rewrite them here. So we have amylase. Amylase is found, it's secreted by your salivary glands in your mouth. Digest carbohydrates. We know carbohydrates are hexagons. This picture shows them as circles, but again, we're breaking them apart. We also have a new one here, lipase. See the word lipid in front of it? Lipid is a fat, so lipase digests fats, which are known as lipids. The pancreas helps secrete lipase. You don't necessarily need to remember that. But remember, we've got our letter E shape, glycerol, and 3 fatty acids, and it's going to help to break that apart. Now, just as a reminder here, we've already talked about bile, and bile is not an enzyme, but bile does help digest things. So as a recap here, bile, remember, breaks down the fats into smaller molecules. So then the lipase, this enzyme, can break them down into fatty acids and glycerol. Here we still have letter E's, okay? The letter E's are still here, but here we're actually breaking them into fatty acids and glycerol. We said the word for that is bile emulsifies. So bile emulsifies fats, and lipase then is actually breaking them into their building blocks. We know pepsin. Pepsin's in our stomach, digests proteins. That one you can remember because pepsin and protein both start with the letter P. We know that the building block of proteins are amino acids. You'll see in this picture, it doesn't quite break them down into individual amino acids. There's actually some other enzymes that help it do that later on. And then an enzyme we're going to learn about today or tomorrow is called renin. And renin is an enzyme that curdles milk. We're going to learn that it's found in the stomach of many newborn mammals. They drink milk. It's also used to make cheese. So you can actually get this enzyme, they produce it in mass production in factories. We can use it to make cheese because in order to make cheese, we've got to turn milk from a liquid to a solid, and this enzyme helps do that. So what it ends up doing is all these little tiny proteins in milk, they're all by themselves, and renin clumps them all together to make a solid. We'll talk more about that later. So the last thing we need to talk about, how do these enzymes actually work? Well, we have what's called a lock and key model. It explains how these enzymes work. If you know anything about locks and keys, if I have a key to my apartment, will it work in the lock of somebody else's apartment? Hopefully not, right? Each key is really specific to its lock. And just like each enzyme has a really specific molecule it's going to use. So pepsin breaks down proteins. Pepsin doesn't break down other things. Its key is the protein molecule. It can't go and digest and break down carbs or fats. So when we're talking about enzymes, okay, I'm going to scroll back to this picture. Actually, I'm going to go to this GIF for a second. Here's what happens. We get a molecule coming in, okay? So our molecule is binding in here. This is the enzyme. So our molecule binds in, this is called the substrate, binds into the enzyme. It's one molecule right now. The enzyme is going to help break it apart so that when it leaves, it's going to be two. And remember, this can go in reverse too. If I have two little molecules going in, they might come out as one because enzymes can help build up or break down things. So the substrate is the molecule that the enzyme is acting on. It's the little molecule that's going to come bind to the enzyme. So in my pepsin example, my protein's going to come and bind to the enzyme because the protein is what's getting broken down. Or in this example, if I have a lipid I want to break down, the lipid is called the substrate. So in your note packet, you can draw, we've got a box here, draw something that looks like this. If it's just a diamond, that's totally fine. You don't need to do this little fancy schmancy thing. You're going to label it substrate. So this is a molecule we need to get broken down. It could also be the molecule that we need to put together. It's going to bind to the enzyme, but only to the special spot on the enzyme called the active site. So it's going to bind in there, and it's like a puzzle piece or like a key fitting into a lock. It has to be the right shape, has to be the right size. So I need you to write down this definition, active site, and then you're going to draw a circle with a little notch cut out, and you're going to label this active site and enzyme. Something you want to note here is that the substrate and the active site have to fit together like puzzle pieces. So go ahead and write that, and then you can draw this picture of them connected together here. And then remember, our whole goal is to break apart this molecule. So the last part here is that we end up with products. So if I'm trying to break down a fat, I'm going to end up with my products of glycerol and fatty acids, the building blocks. And again, you can draw this and show the two products leaving. So that's how enzymes work. Substrate goes into the enzyme, binds to the active site, has to be the right size and shape, and then gets released as products.